Welcome to this video with an example of analyzing determinate structures. This is one of several videos in a short course on equilibrium posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. The frame considered in this example is statically determinate and similar to the portal frame addressed in a video posted adjacent to this one at terje.civil.ubc.ca Toolbox. However, we will learn more in this example about joint equilibrium, because column CD is now inclined. Also, the load is here arbitrarily selected to be acting vertically on beam BC. Following the standard procedure for determinate structures, the reaction forces are first calculated. These are the three equilibrium equations at our disposal, leading to these reaction forces. Notice that the horizontal reaction force at the pin support at point A is 0 because there are no horizontal forces acting on the structure. The second step is to calculate the bending moment at selected locations. The moment is 0 at point A and point D. We find the bending moment at point B by cutting the frame there and holding column AB with our hand placed at point B because there are no forces acting perpendicular to this member. The bending moment value at point B is actually 0. Again, notice the procedure, using equilibrium after we cut the structure. Some students try to guess the deflected shape of the structure and speculate about how the bending moment diagram might look like. That is an error-prone approach. It is better to use equilibrium explicitly. Remember, equilibrium is all we need for statically determinate structures in order to determine the internal forces. Next, we find the bending moment at point C. The reaction force at point D times the distance 4 meters give a moment near 13 kN/meter. As we did in earlier videos, we now draw lines between those moment values we found. The distributed load acting on beam BC means that we add the QL²/8 parabola like this. The next task is to determine the shear force diagram from the bending moment diagram. There is no moment in the vertical column on the left, so we start by addressing the horizontal beam. Notice that the bending moment diagram is comprised of a triangle with tension at the bottom and a parabola with tension at the bottom. The shear force diagram that corresponds to a triangular bending moment diagram is a constant, with value equal to the change in moment divided by the member length. It is a downhill walk on the bending moment diagram, so this is positive shear. The shear force diagram corresponding to the QL²/8 parabola is this double triangle shape, as we know from the basic case of a simply supported beam. That means the final shear force diagram for the horizontal beam BC looks like this. The shear force diagram for the inclined member CD is relatively easy to determine if we have watched the previous videos and recognize that there is no load acting along this member. The axial force in column AB is determined in a manner very similar to what we saw in the previous video on a portal frame. The 11.8 kN shear force in the beam pushes down on the column. As a result, the column is in compression. The axial force in the horizontal beam BC is 0 because there is no shear force in column AB. Now to the hard part. What is the axial force in the inclined member CD? To find the answer, we consider equilibrium of forces at point C. We already know the 3.21 kN shear force in the beam at point C and the 2.27 kN shear force in the inclined member CD from the shear force diagram. Those forces are included in the summary of forces acting at point C shown on the left-hand side of this page. Question marks are highlighted for the other forces acting at this point, namely the axial force in the members coming into point C. We already know that the axial force in the horizontal beam is 0, so this horizontal force will turn out to be 0. That is indeed observed in this force polygon. The vertical 3.21 kN force is first laid down on paper, followed by the 2.27 kN force. The 2.27 kN force that closes this force polygon is the axial force in the inclined member CD that we are seeking. Notice that it pushes up towards point C from the lower right, so this is a compressive force that should have a minus sign attached to it in the axial force diagram. Notice that we now used knowledge from the video on the equilibrium of forces at a point. The axial force diagram at the bottom of this page summarizes the information we just calculated. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.